Let me move this over. All right. Oh, Ivan, are you still there?
Oh, all right. I can see you now.
Okay. All right, so let's get started. Good morning, hello. Again, thank you for braving the cold and welcome to everybody that is joining us on the live stream. A couple quick announcements. So as a reminder, our next mini quiz and homeworks are due on Sunday. So make sure you're keeping an eye on that. There is drop-in help available today and Sunday. If you have questions from the homework, you can certainly stop by and get help on that. So I want to mention that today we're going to be talking about new functions from old, and we are going to be focusing on the composite function aspect of this. There's also a small subsection on graphing transformations. If you remember how to do those, then you should be good, just moving graphs up, down, left, and right. But if you don't, you should check out that video on Moodle just to sort of remind yourself of how graphs move and change. And that is also what the review is on later tonight. So that is something you want to make sure you understand, because that will be part of many of the things we do. And so if you don't remember that, then you should go ahead and check that out. Also, I wanted to mention our supplemental instructor is going to be starting SI sessions next week. Those are in person in the library. There's actually 2 SIs for this course, and so the times for those are posted in Moodle. So you'll see, I believe that there's one on Sunday, Monday, Wednesday, and Thursday in the library, and those are just a weekly review of the things we're doing in class with some extra practice problems. So if that's something you're interested in, you can find the time and location posted in Moodle. I don't think I have any other announcements, so I'm going to go ahead and switch to the dot cam. Okay. And so like I mentioned today, the sort of big picture overview is new functions from old. So when we talk about creating new functions and transforming them in different ways, there's a lot of different things we can do. But I want to remind you, the sort of process is that we're going to take what we know how to do and then start applying it to what we don't know how to do. So let's start with just the general definition of what is called a composite function. So a composite function are the pointwise applications of one function to the result of another function, which results in a third function. So what does that mean? That means that we are taking one function and plugging it into another one. And there's sort of 2 different notations that are used when we talk about composite functions. Sometimes you see this f and then this little open dot g of x. And sometimes you see it written as f of g of x with the parentheses. In this class and in our textbook and stuff, you will notice that this is the notation we will be using. But if you've seen this before and the notation was like this, it's the same thing. Okay, so we're going to start with a little exercise to sort of think about what we know how to do and then build up to what we don't know how to do. And so for example 1, I want you to think about how we would calculate f of 2. So I want you to actually write out the steps of where you would plug things in. And then I want you to think about what that would mean if we did the same thing, but instead of a 2, we had an h, right? So what would that look like? Is that going to be a number? Is that going to be a function? And then thirdly, we're going to plug in h plus 2 and see what kind of result we get. Okay, so I want you to take 2 minutes and I want you to do 1, 2, and 3. First plug in the 2, then the h plus 2. And our function f of x up here is x squared plus 3x minus 4. So go ahead and try that out. I'm going to give you 2 minutes. Just jot down what those are going to look like, and then we'll go through them and talk about why it's relevant for what we're doing here. Okay, take about 30 more seconds. All right. So when we talk about f of 2, hopefully you remember from what is a function that when we see something in here, we're going to plug that in wherever we see the variable. So we're going to have 2 squared plus 3 times 2 minus 4. We're simply substituting in a 2 every time we see an x. Then when we crunch this number, we're going to get 4 plus 6 minus 4. So I just simplified each part. The 4s are going to cancel, and we get a numerical output. So when we plug a number into a function, we get a number out, okay? So what happens if we then plug in an h, right, like a variable? So again, wherever we see an x, we have h squared plus 3h minus 4. We don't have like terms to combine here, so what we end up with now is another function, okay? So we have a function here, we have a number here, okay? So we plug them in the same way. So no matter what you see inside the argument, that's what you plug in for x. So if we take it a step further and we do h plus 2, we're going to get h plus 2 squared plus 3 times h plus 2 minus 4. Now, in order for us to think about if there are like terms to combine, we're going to have to do a little algebra to square this out so we can see what terms are similar here, okay? So I'm going to do it right underneath. So h plus 2 squared means we're going to do h plus 2 times h plus 2. So we're going to be foiling that out, right? So that's going to give us h squared plus 4h plus 4. And then the second term, we're going to distribute the 3 to both terms. So 3h plus 6, and then we still have our minus 4. So now we can look at and combine like terms now that we've squared everything out so that we have terms we can consider. So there's only one h squared term. And then we have a 4h and a 3h. So 4h plus 3h gives me plus 7h. And then for my constants, I have 4 plus 6 minus 4. So that's going to give me plus 6. Okay, so again, we notice that we end up with a function for an answer. So whenever there is a variable that you are plugging into your function, you are expecting a function answer. If you are simply plugging in a number, you're expecting a numerical answer. Okay, so what we want to do is we want to start thinking about this idea of plugging different types of functions into another function, which is what we did in steps 2 and 3. Step 3 was a little more of what we will be doing. So we're thinking about what we're plugging in, where it goes in terms of the variables, and then simplifying to see what happens. So let's try another one. So consider the function m of z equals z squared plus 2. So again, usually we have x's and t's as our variable, but there's nothing that says we have to. So z could certainly be our variable. So we want to take this original function and use it to find m of z plus 1 minus m of z. So in order to be able to do this final step of subtracting these two functions, we need to find each of these functions separately. So I want you to find m of z plus 1 first. Then I want you to find m of z. And then I want you to find m of z plus 1 minus m of z. So once you've found these two functions, you can subtract them. Okay, so take another 2 minutes. Again, anything that is algebraically unclear, you're going to want to simplify so you can figure out how to combine like terms. Okay, so again, we're expecting a function as our final answer, and we expect that function to have z's in it because we're dealing with the variable z here. Okay, so take 2 minutes and then we'll go through it together. Okay, take about 30 more seconds to finish up whatever part you're working on. Okay, so again, we want to find each of these separately and then put them back together to solve the final question. So m of z plus 1 means we're going to take a z plus 1 and plug it in wherever we see a z. So we're using the same variable as what's in here, which is a little tricky, so we just have to be careful about that. So that means we're going to have z plus 1 squared plus 2. Right? And again, in order to be able to simplify this, we're going to want to FOIL out that first term. So when we multiply that first term out, we're going to get z squared plus 2z plus 1. And then we still have this plus 2, right? So this was the FOIL, and this was just our plus 2 from before. So now we can combine like terms. So I look across and I see that I have 1z squared, so z squared. The only z term is the 2z. And then I can combine the 1 and the 2. And that gives me plus 3. So m of z plus 1 is going to give me z squared plus 2z plus 3. Okay. Now I also want to find m of z. Now, this might be a little confusing because m of z is what we are given, right? Which means we're not actually substituting anything in. Instead, we're just getting the same thing back, z squared plus 2. Okay, so the m of z is the original function. So now that we have m of z plus 1 and m of z, we can subtract them, right? So m of z plus 1 minus m of z is what we're trying to find, right, from our question here. So we're going to substitute in what each of these things equals once they were simplified. So that means I have z squared plus 2z plus 3. That's my m of z plus 1 minus m of z. But I want you to notice that m of z has 2 terms. So I'm going to use parentheses because that minus has to go to the entire function. Okay, So now that I have my two functions, I can subtract them, I can combine like terms, and I can simplify to get my final answer. So I start with the z squareds. I have a positive z squared and then a minus z squared. So those are going to cancel. Then I have 2z as the only z term. And then I have 3 minus 2. So 3 minus 2 is going to leave me with a 1. So my final answer to the problem presented is 2z plus 1. Okay, so again, if you are looking to subtract or add or multiply functions, you want to find their individual pieces first and then put them together to answer the question. Okay, so this is just practicing plugging functions directly in by saying what that function is going to be inside the argument. The more common way that we are going to start to see composite functions is that we're going to have a couple of functions defined, and then the composition that we're supposed to do is going to be presented to us, and we will have to take the step to plug it in. So let's look at that and see what that looks like. Okay. So in this first example, we're going to consider 3 different functions. Okay, f of x equals x squared, g of x equals e to the x, and h of x equals the square root of x minus 2. So there's a whole bunch of compositions that we're going to try to find here by putting together these different types of functions. So we're going to do the first one together, and then I'm going to have you try some of these. So for the first one here, we have f of g of x. So what does that mean? That means that we are taking the g function and plugging it into the f function. So there's a couple different ways that you can set this up to do this. It's really sort of a matter of preference, but I'm going to show you how I think about it, and hopefully it makes sense to you. But if you've learned it a different way or think about it a different way, that's okay. So we're trying to plug the g function, which is e to the x, into the f function. So when I do f of g of x, what I would do is I would rewrite my f function with a literal g in it first, because this is how I was taught to do it. So instead of an x, I'm going to write g of x squared. So I'm doing a literal substitution of g of x into the x variable. Another way you can think about this, okay, is f of g of x, you could write as f of e to the x. You could plug the function in here first and then plug it in. That'll be the same thing. So once I have my g in all the right places, then I'm going to take the step to plug the g function in. So the g function is e to the x. Okay, so let's do that in a different color. So once we plug in that function, we have e to the x squared. Okay, so now we need to think about what that means algebraically. If you have a power raised to a power, so e to the x is the first power, but then that's raised to the 2 power, you multiply those 2 powers together. So this is e to the 2x. Okay, so what I'm saying is, alternatively, one way you can think about it is you can think about this first function as f of e to the x, right? So you can write it, the g function, right inside, and then you can see how you're plugging it in. That's the second way you can think about this, and you end up with the same thing, right? Because then you do e to the x squared, right? And then you end up with e to the 2x. So what I want you to try to do is I want you to try these other functions, and I'm going to give you a quick hint about a few of these. So when you do g of f of x, that means you are plugging the f function into the g function. So that's the opposite direction of plugging in. So you're plugging in an x squared into e to the x. H of f of x, you're plugging f of x into h. So notice that there's an inside function and an outside function. H of x means you're plugging the function into itself, right? Which is a little weird. So you want to think about how that might work. And then for the last one, f of t of 1 times g of t. So this is something where we're dealing with 2 different functions, and then we're doing an operator on them, which is multiplication. So this is another instance where you're going to want to find f of t of 1 first, and then g of t, and then multiply the two of them together. So finding each of these separately since there's two functions. Okay, so I'm going to give you about 4 minutes. I want you to try these out. See if you can think about how you plug these in based on the order. Remember, the inside one gets plugged into the outside one, and then we'll go through it together. Feel free to check in with someone nearby to you, and the TAs will come around. If you have any questions, you can certainly ask them, but we'll go through it together in about 3 to 4 minutes. Okay, take about 30 more seconds. All right, so let's go through these. And again, there's a couple different ways to do this process. So if you did it, in one way and I did it slightly different, as long as we're coming to the same conclusions, then we should be good. Okay, so the next one we are going to try to do is g of f of x, which means we're plugging the f function into the g function. So again, what I like to do is I like to write the g function with the literal f of x in it. So I write e to the f of x, right? I just plug it in where I see it. Again, you can write it slightly different. And then I go ahead and plug in what f of x actually is. So here I would then go to my f of x, which is x squared, and I get e to the x squared. Okay, so I want you to notice here that these are different. They're similar, e to the 2x and e to the x squared, but they are different. And so one of the main takeaways here is that we want to realize that f of g of x is different than g of f of x, so that the order is important. You can't go sort of willy-nilly plugging in things however you want. You have to do it in the order that's listed in the problem, right? So that you don't get the wrong answer. So let's look at the next one. We have h of f of x. So that means we want to take the h function. And so here, instead of x, I'm going to write f of x minus 2. And then I'm going to go ahead and plug in for my f of x. And again, if you're comfortable skipping this step, that's totally fine. I like to write everything down in case I make a mistake. So here, my f of x is x squared. So I have x squared minus 2. Okay, so again, my f of x function, x squared, goes in for the x that's in the h function. So now we're going to look at h of g of x. So again, I'm going to start with my h function. I'm going to write g of x. And then I'm going to go ahead and I'm going to plug in what g of x equals. So here, my g of x is e to the x. So I have the square root of e to the x minus 2. Okay. So again, I'm keeping in mind what is the outside function, what is the inside function, so that I know how to plug it in. So now the last two are a little bit trickier. So if you didn't get to them, that's totally fine. But if you did, let's see if you were able to figure out how we plug these in. So h of x means we're taking the h of x function, which is the square root of x minus 2, and we're plugging in h of x wherever we see an x. So we end up with the square root of h of x minus 2. Now, h of x is the square root of x minus 2. So instead of h of x, I'm going to write the square root of x minus 2 and then minus 2. So I'm substituting that function in that spot for h of x. It's a little bit goofy when you plug things into themselves. So you just have to be careful about making sure you don't miss any pieces or make assumptions. Okay, so now for the last part, we're going to do f of t plus 1 times g of t. So as I mentioned, we're really going to want to find each of these things separately and then put them together. So f of t of 1 means we're going to go to the f function and we're going to plug in a t plus 1. So we have t plus 1 squared. Okay, if we multiply that out, we get t squared plus 2t plus 1. And then we also need g of t. So g of t, we're going to go to the g function and we're going to plug in a t everywhere we see an x. So e of t. So then we need to multiply those two things together. So when we multiply them together, I'm going to use parentheses for this first part because there's more than one term. So when we multiply them together, we're going to get t squared plus 2t plus 1 times e to the t. And you could certainly have the e to the t in the front. Multiplication 2 times 3 is the same as 3 times 2. So that order is not important. But what's important is that you have the parentheses around the entire f function because it's the entire function that's multiplying the other term. Okay, so we get something that looks like this. So hopefully you're starting to get the idea of how we plug things in as we go. Now, another thing that we are going to be doing is we are going to be looking at composite functions at a particular point. So when we do this, I want you to notice that the innermost thing that we see is the variable x. And again, we said when you plug in something with a letter, you expect a function as an answer. Sometimes we want to know the composite function at a particular point. Okay, so here we have the same functions we had before, x squared, e to the x, and the square root of x minus 2. And now we want to consider a composition at a particular point. So we're considering f of g of 0, g of f of 0, h of f of 3, h of g of 1, h of 6, and then f of 3 times g of 0. So there's sort of two distinct ways that we can approach this. We can either take the composite function that we found in the first part, right? Match them up. So f of g of 0, we would find f of g of x, and we'd plug in a 0. Okay, so that's one way to do it. The other way you can think about it is you can find g of 0, right? So you go to the g function, you find g of 0, you get that value, and you plug that into the f function. Okay, so we'll do the first one together using both methods so you can sort of see the difference, and then you can try the other ones. So for f of g of 0, the first method would be to take f of g of x, the composite function, which we did up here, which was e to the 2x, and then say, okay, then f of g of 0 is e to the 2 times 0. Now, 2 times 0 is 0, and then you'll have e to the 0. Anything to the 0 power is 1. Okay, so you can compute it based on the composite function. The alternative way is that you could start in the middle and find g of 0. So you go to the g function, you have e to the 0, e to the 0 equals 1. So then you plug in a 1 here. And so now you're going to do f of 1, right? Because you're substituting in what g of 0 equals. And so now you go to the f function, and you have 1 squared, which equals 1. Both methods are going to give you the final result of 1. I will mention when you decide to do one method over the other, it really doesn't matter. You're going to get the same thing. So if you have a preference, that's fine. But typically, if we are doing composite functions at a point and you don't already have the composite function done, then typically this is a little bit easier to plug in starting in the middle and work your way out. If you do have the composite function already done, then it's about equal, in terms of figuring out the final answer. So it's really up to you. Okay, so I want you to try these other ones. We have g of f of 0, h of f of 3, h of g of 1, h of 6, and f of 3 times g of 0. Okay, and so I'm going to give you 3 minutes, see if you can find those values, and then we'll go through it, and I'll just alternate the method we use. So we'll do some where we use the composite function from above, and some where we start from the inside and work our way out, so we can get comfortable doing it both ways. But try to get those values. If you have enough time, go back and do it in the other way, since there's 2 methods, to make sure you're getting the same thing. Okay, and then we'll go through it together. So give it a try. Feel free to check in with someone next to you, and then we'll go through it in just a few minutes. Okay, take about 30 more seconds. All right, so let's go ahead and look at these. And again, we'll just alternate the way that we go through these. So let's start with the composite function and plugging in. Oops, so we were doing g of f of 0. So we start with the composite function g of f of x, which we did before up here, which we found to be e to the x squared. So when you have the composite function, you can go ahead and plug in the value that you're interested in. So here we would plug in the 0 directly for the x. 0 squared is 0, and e to the 0 equals 1. Okay, so whether you did this method or the from the middle out method, you should be getting a value of 1. Okay, when we look at the next one, h of f of 3, we'll do this one from the inside out, so we can just alternate methods here. So we would start, if we're doing the other method, by finding f of 3, so the innermost function. So f of 3 means we're going to go to the f function and plug in a 3 wherever we see an x. So 3 squared is 9. So that means we're going to substitute that in. Instead of f of 3, we're going to plug in a 9. Okay, so that means we're looking for h of 9. So we're going to go to our h function. And then wherever we see an x, we're going to plug in a 9. So we have 9 minus 2. So that's going to give me the square root of 7. Okay, so we started with the innermost, we got that value, we plugged it in, and then we found the outer function at the value we had found for the inner function. For h of g of 1, we can go ahead and go back to the composite function. So for h of g of x, okay, we go up, we said h of g of x, our function was e to the x minus 2 under the square root. Okay, so if we're going to plug in a 1, h of g of 1, we go ahead and plug in a 1 for the x value. So you have the square root of e to the 1 minus 2. Okay, we're going to leave it like that. You can write it as just e if you want, because anything to the 1 power is just itself. That means the same thing. For h of 6, we're going to go ahead and go from the middle and work our way out. So we start by finding h of 6, right? This inner value. So h of 6, we come up to our h function. We have the square root of 6 minus 2, which is the square root of 4, which we know is 2. And then we're going to plug that into the outer function. So now we're looking for h of 2, which is the square root of 2 minus 2. 2 minus 2 is 0. The square root of 0 is 0. Okay, so again, for this one, I started in the middle, worked my way out. And as I mentioned before, you can do either process for any of these. I'm just alternating just to make sure you understand both processes. So if you did a different process, that's fine. You should have the same answer. So for the last one, we have f of 3 times g of 0. So this one is a little more tricky because we can't just use the composite function because this is not a composite. This is a product of two functions to get a new function, right? Which we got up here. But since we're not plugging one into the other one, we do have to find these separately. Okay, so f of 3 means we're going to take 3 and plug it into our f function. You can plug it in to the simplified version. You can plug it into the t plus 1 squared version. Either is fine. But when we plug in a 3, we're going to have 3 squared plus 2 times 3 plus 1, right? 3 squared is 9. 2 times 3 is 6 plus 1. So that's going to give us 16. Okay. Then g of 0, we're going to go to our g function, which is e to the x. We're going to plug in 0. So we have e to the 0. Anything to the 0 power is going to be 1. So this gives us 1. Now we want to multiply together f of 3 times g of 0. So 16 times 1, if we multiply those together, it's going to give us 16. Okay, so I want to point out that this one is slightly different because this is not a composite function. We're not plugging one thing into another one. We do have to treat each piece separately and do it with that method since we're not plugging into one another, since there's more than one thing we are plugging into. In these scenarios, we end up with one x value, so it's okay to plug it directly into that. Here, we have 2 different places we're plugging in, and we're multiplying together, so we have to treat them separately. Okay, so thinking along the same lines, we've been looking at situations where we have algebraic functions, and I will say that the majority of the time we will be working with algebraic functions, but there's other ways that we can also think about composites. So another way that comes up is with tables. So I want to talk about how we think about and evaluate functions when we have a table. Okay, so as we thought about back in chapter 1.1 or section 1.1, we talked about tables and how the independent value is the first line and the dependent value is the second line. Now this table has 4 lines, and so I want to point out that the way this is set up is that the independent value goes across the top, and then the dependent value for each function is listed across. So there's 3 different dependent values depending on the function you are talking about. So we can look at composite functions and think about them if we have a table of values. And so if we do that, we are not composing any functions because we don't know what the functions are in terms of their algebraic qualities, but instead are considering the values of each of these functions at a point. So we're going to do an example together, and then I'm going to have you try these. And so the example that we're going to do together, I'm going to write it above, is f of h of g of 2. Okay, so if we had a function like this, how would we start? We start on the complete inside with the g of 2. Okay, so when we do g of 2, that means that 2 is the independent value. So we go to the top row and we find the 2. And then we go down to the G row, which is the middle one, to find the dependent output. Okay, so that's going to give us a 4. So what we're going to do is we're going to take that 4 and we're going to plug it in where that G of 2 was, right? So instead of G of 2, we put in the value that we calculated, which is 4. And that creates a new function now. So now we have h of 4 as the innermost function. So we go ahead and compute h of 4. So again, we go to the 4 in the top row, and then we go down to the h value. Okay, so the h value here is going to be 1 when x was 4. So instead of h of 4, I'm going to substitute in the value, which is 1. And then ultimately, I'm left with f of 1. So f of 1, I go to the independent value of 1, I go down to the f function, which gives me a dependent value of 2. So when you're working on a table, you're looking for values because we have a value in the middle, a number, and you're going to start in the middle and work your way out. Okay, so I want you to try these 3. We have f of g of h of 1. We have G of G of G of 1, and we have H of G of F of 1. Okay, so we have a triple composite. So I'm going to give you 2 minutes. I want you to try these 3, write out the steps that and numbers you're getting along the way, and then we'll go through them together. Okay, take about 30 more seconds. Okay, so again, we want to start in the innermost calculation. So H of 1 is the first part we're doing. So to find H of 1, we go to the 1 in the independent row, and then we're going to go down to the H function, which gives us 1. So that means that now we're looking for F of G of 1, because that value is 1, so we substitute in H of 1 for 1. So now we're looking for G of 1. So for G of 1, we again go to the 1 in the independent row, but now we go down to the G value. Well, that value is 3. So we're going to substitute that in, and we have F of 3, which means we're going to go to the 3 in the top row and then go down to the F value. So the F value here is 0. So F of G of H of 1 equals 0. So if we had this composite function, if we knew all 3 of these functions and we were able to make this composite function and we evaluated what was happening at 1, the dependent value would be 0. Okay, let's look at the next one. So we have G of G of G of 1. So we're composing something with itself. So G of 1 means we're going to go to the 1 in the independent row and go down to the G function, which is going to give me a value of 3. So now I have G of 3. So the next thing I have to find is G of 3. I go to 3 in the independent row, and again, I go down to the G function, and that gives me a value of 4. So now I have G of 4. So ultimately now I'm looking for G of 4. So I go to the 4 in the top row, I go down to the G value, and I get a value of 2. Okay. So again, I'm just working from the inside out to compute these values. For the last one, H of G of F of 1. So F of 1 is the innermost part. So I go to the 1 and I go down to the F function to get the dependent value. That's going to give me a 2. So I have H of G of 2. So now I'm looking for G of 2 is the next innermost value. So I go to the 2, I go down to the G function. That is a value of 4. So I substitute that in. I have H of 4. And so finally, I go to the 4 in my row. I go down to the H function, and I have a 1. Okay, so no matter what the composition is, if you have the table, the idea is that you want to start on the inside and work your way out, right? Whatever the innermost evaluation is, you find that number and then you keep working, okay? So hopefully that makes sense on what we're doing with tables here with composite functions. Sometimes you only have to do 2 rows like F and G, but sometimes it's 3 functions, okay? So the next sort of application we're going to consider here is a word problem. And so in word problems, one of the things that we really need to practice and get good at doing is making sure we understand what we are trying to find. So here, I'm going to try not to give you too many hints here. So I want you to think really carefully about what the dependent and independent variables are going to be for your final function. So we have the formula K of C equals C plus 273, which converts Celsius temperatures to Kelvin. So Kelvin's just another measurement of temperature, if you didn't know that. And then the formula C of F equals 5/9 times F minus 32 converts Fahrenheit temperatures to Celsius. So we want to write a composition function that will convert Fahrenheit temperatures to Kelvin. So think about what that means in terms of what is the dependent and independent variable and how you might structure that. And then for part B, we want to convert the boiling point of water, which is 212 degrees Fahrenheit, and the freezing point, 32 degrees Fahrenheit, to Kelvin. So you have to have the right equation in part A for part B to work, but try your best. So I'm going to give you 2 minutes to think about how we can set up this composite function. And then if you are able to figure it out, then for part B, you should be able to plug in those values and evaluate them like we have been looking at a particular point. Okay, so take 2 minutes and then we will go through it together. Okay, take about 30 more seconds. Okay. So we have 2 functions here, one for Kelvin based on Celsius and one on Celsius based on Fahrenheit. And so you probably have a pretty good idea that we have to compose these 2 functions. And so the question is really, which direction do we compose them? Only one really makes sense when you try to do this, but there's certainly a lot of ways we could stumble upon a wrong direction. So we really need to look at the wording here. We want to convert Fahrenheit to Kelvin. That means we are plugging something in for Fahrenheit and getting something out in Kelvin. So that means that Fahrenheit should be our independent variable and Kelvin should be our dependent variable, our output. So that means that when we think about this, since we're trying to plug into the Kelvin function, Kelvin should be our outermost function. Okay, so we have Kelvin But in order to get Fahrenheit, we have to plug in the function C of F, right? We have to plug the Celsius function into Kelvin because it's the Celsius function that brings in the Fahrenheit, right? So when F is in the middle of your composite function, that means that F is going to be your independent variable, which is what we want, okay? So when we plug the Celsius function into Kelvin, it's nice because the C is just a C. We're not doing anything to it. So we can just plop the whole function in there. So we have 5/9 times F minus 32 plus 273. Okay, so you have a choice at this point for the conversions. You can leave this like this, or you can multiply the 5/9 through and combine the constants. I'm going to leave it like this just because this fraction is not very nice, so we can't really simplify it or turn it into a decimal because it's irrational. So I'm just going to leave the function like this. Okay, if you simplify it, that's fine, but you should have a fraction here, 160/9. And then you would need to convert this to ninths to add it together. It's up to you. So for part B, we're converting two numbers. We're doing the boiling point and the freezing point. So let's start with the 212. So we're looking for, okay, a C of 212, right? To go from Fahrenheit to Kelvin. So that means that we are plugging in a 212 for F. So we have 5/9 times 212 minus 32 plus 273. So you can see that I'm plugging it directly into the composite function. You could also plug this into the Celsius, get that number, and then plug that one into Kelvin, right? That's the other method, those two methods we've been looking at. You'll probably do this on your calculator, because I did, and you will get 373. This will be in Kelvin. So I'm going to put a C for Kelvin to remind myself that I'm going from Fahrenheit to Kelvin. Okay. Similarly, if we wanted to convert the freezing point of water, we're going to be plugging in 32 for F. So we have 5/9 times 212 minus, oh, no, wait, what did I do? Oh, no, 32. 32. I don't know why I said 212 again. 32 minus 32 plus 273. So we can see that this is going to zero out 32 minus 32. And so we just get that Kelvin is 273 degrees Kelvin. So the freezing point of water in Kelvin is 273 Kelvin, and the boiling point is 373 Kelvin. So we were able to convert because we had formulas for both Celsius and for Kelvin that allowed us to bring in the Fahrenheit to create this composition function. Okay, so setting up composition functions is one of the more complicated things that we have to do. We don't do it a lot. Most of the time they're given to you, but there are a couple on homework where you really need to think about what's happening in the problem. And so you can figure out the order of what you're plugging into what based on the scenario and what makes sense. So I find it helps to think about what is your independent variable and what is your dependent variable to try to figure that out. Okay. So the next thing we talk about is domain. So we have these two functions and we're putting them together for some particular reason. And so that can impact the domain of the composite function. So if you are just given a function with no context, right, the domain is whatever sort of restrictions are naturally imposed by the mathematics, right? So we know we don't want to divide by 0. We know we don't want to take the square root of a negative number, things like that. But when you have domains of composite functions, you have to consider the original functions as well as the composite functions, because in this context, we do know that we're composing them for a reason. Okay, so how do we do that? We find the domain of the inside function that we're plugging in, and we write down any restrictions that they might have on that function that we are plugging into the outer function. Then we're going to construct the composite function, right, by plugging it in and simplifying, and then we're going to find the domain of the new composite function. Okay, if there's restrictions on that domain, we're going to add them to the restrictions we had from the original function we plugged in. If there's an overlap, then we're going to use the more restrictive domain. Okay, and we'll take a, we'll look at this and see what that means overall. So we have to consider again the original function that we're plugging in and the composite function, and then we're going to take the more restrictive domain. So same functions we were working with before. Oh, my f disappeared. So f of x equals x squared, g of x equals e to the x, h of x equals the square root of x minus 2, and we want to find the domain and range for the composite functions. So again, the first thing we want to do is we want to think about the composite function that we're finding, and we want to start by considering the inside function. So g of x is the inside function for this f of g of x. So g of x here is e to the x. So the inside function is e to the x. What is the domain of e to the x? Well, e to the x, you can plug anything into. There's no restriction. You can plug in positive numbers. You can plug in negative numbers. You can plug in 0. E to the x is fine for all of those. So the domain for the inside function is just x from negative infinity to infinity. We can plug in whatever we want, okay? The new function is the function we get by doing the composition. So we already did these in the first example, so you can reference back if you don't remember. But when we plug e to the x into x squared, that's when we got e to the 2x, okay? So now we consider what's the domain of this new function, right? Well, the domain of e to the 2x is the same as the domain of e to the x. We can plug in whatever we want. So we have x could be anything from infinity or negative infinity to infinity. So that means that the domain of the composite function, we have to consider the more restrictive domain, but they're the same, right? One is not more restrictive than the other, which means that the domain of the composite function is negative infinity to infinity, okay? So we're going to try this for some of these other compositions. They get more complicated as you go down the line. So I want you to try your best to try to think about what these domains might be. Just do what you can. We'll see what happens. And so I'm going to give you about 2-3 minutes, and then we'll go through them together. Okay, take about 30 more seconds. All right. So again, we want to start by looking at what the inside function is and consider the domain of the thing we're plugging in. So f of x, the inside function is x squared. Fortunately, we're starting off strong. X squared, we can plug in whatever we want, right? The domain is all numbers. There's nothing we're worried about plugging into x squared. Then we come up with our composite function. Again, these are the composite functions we constructed in the first example. So we end up with e to the x squared. So we know that e to the x, we can plug in whatever we want. So e to the x squared, we can also plug in whatever we want because we're still going to get positive numbers and 0, which is totally fine. You will always get a result with no algebraic issues. So the domain of the new function is also negative infinity to infinity, which means the domain of the composite function is negative infinity to infinity because one is not more restrictive than the other. Okay, so far we've had situations where everything just is fine. We can plug in whatever we want. Now for the next one, we start with the inside function, f of x. We have x squared, great. We can plug in whatever we want to x squared, no problem. But now we have the situation where our composite function is the square root of x squared minus 2. So hopefully you remember with square roots that you can't take the square root of a negative number. Okay, so that means that the domain of the composite function is going to be a little more restricted. So I'm going to do some work down here. So I know that x squared minus 2 has to be greater than or equal to 0. Okay, I can take the square root of 0, that's fine, so I can use the equals. So that tells me that x squared has to be greater than or equal to 2. And hopefully you remember inequalities from whenever you took algebra a long, long time ago. But if you have x squared is greater than or equal to 2, then what that tells us is that x has to be greater than the square root of 2 or less than the negative root of 2. Okay, so as long as x is bigger than the square root of 2, then the x squared term is bigger than 2. And also if it's less than negative square root of 2, it's bigger than 2. So these are the conditions that are going to allow for the stuff under the square root to always be positive. So the new domain is that x has to be greater than the square root of 2 or less than negative square root of 2. Okay, so as long as that happens, right, we are good to go. So comparing these two domains, clearly this one is more restrictive. So that means that the composite domain is that x is greater than the square root of 2 or less than negative square root of 2. Okay, that's our domain for this one. So we can see that the domain of the new one is more restrictive. So that's what we get for the composite function, which is typically the case, that the new domain ends up being more restrictive. For e to the x, right, our inside function for the next one, g of x is e to the x. We can plug whatever we want in. No problems there. But now we encounter something similar here. We don't want the square root to be negative. So we have e to the x minus 2 has to be greater than or equal to 0, which means we need e to the x to be greater than or equal to 2, right? And so how do we deal with that? Well, hopefully, again, when you learned inequalities, you talked about exponential functions. So because this value is greater than 1, we can take the natural log of both sides. So we get x has to be greater than or equal to the natural log of 2. Okay, so this is only true because this is bigger than 1. We have to be really careful if it's less than 1, right? Going back to things we know about natural logs. So here, the domain is x is greater than or equal to the natural log of 2. When comparing the two domains, this one is more restrictive. So that's the one we get for the composite function. Okay. That one's a little tricky. People often forget how inequalities work with exponentials and logs. So if you did, that's fine, but you can test it out by plugging in some practice numbers and convince yourself that that's true. And then our final one here, we have x minus 2 under the square root is our inside function. So we actually start with a more restrictive domain than we have before. So in that case, x minus 2 would have to be greater than or equal to 0. So that means x has to be greater than or equal to 2. So if x has to be greater than or equal to 2 is the domain of this inside function. Now, once we have our composite function, we have the square root of the square root of x minus 2 minus 2. So this is where we need to do a little algebra on the side. So now we take this part, right, the inside part, move this up a little bit, and we have the square root of x minus 2 minus 2 has to be greater than or equal to 0, right, because this is inside. So we can move the 2 over. So we have the square root of x minus 2 is greater than or equal to 2, okay? So what we're going to be doing is we're going to be squaring our function, right, on both sides so that we can figure out what these values need to be, right? So then we end up squaring both sides. So we have x minus 2 is greater than or equal to 4. When you square a square root, it goes away, right? We're taking the positive roots here. So we add the 2 over and we get x is greater than or equal to 6. Okay, so by x being greater than or equal to 6, it guarantees that this will be bigger than 2, which guarantees that this will be positive. So here we have x is greater than or equal to 6. When we compare these two domains, x greater than equal to 6 is more restrictive because that says we can't use 2, 3, 4, and 5. So that is the one we adopt here. Okay, so again, you're going to go through piece by piece and take the more restrictive domain. Just a couple of comments about the two examples we didn't get to. The first is that sometimes composition fails, right? You can't plug negative x squared into the natural log of x because the natural log of x is not defined for negative numbers. It doesn't happen often, but there are times that you can't do composition at all. And that's when you look at the domain of the function you're plugging into. And then if the function you're plugging in violates the domain, you can't compose it. And then the second thing is sometimes we start with a composition function and we want to try to think about what the original functions were. And so just one quick example, we could break this down into f of x equals e to the x and g of x equals, what's that say, 2x minus 3. And then this function would be f of g of x. Okay, so sometimes you want to be able to look at a composite function and think about what function could be plugged in. Just one last quick example. This one we could break down into the square root of x, and g of x would be natural log of x plus x. Okay, so think about how you could break things down into two functions. There's more than one right answer for a lot of these, but you'll do a couple on homework. So you're just thinking what could be an inside function, what could be an outside function to make the function I'm looking at. Okay, so that's composite functions. Again, if you haven't done graphing in a while, stop by the review tonight or watch the graphing video. Otherwise, you should be good to go for Sunday's homework and mini quiz. Have a great rest of your day.